Okay, good morning, ladies and gentlemen, distinguished guest on the dais, uh, President of KJ College of Engineering and Management Research, Professor Principal Swas Kotsar, convener of this ST, STP, STTP short-term program, Prajakta Deshmukh Madam, Coordinator Vivek Purade sir, esteemed participants and fellow enthusiasts of advanced materials. I joined for this online program with you today with a great enthusiasm and anticipation as on embark on a short-term program focused on recent developments in advanced materials. In a world that is constantly evolving, innovation becomes the cornerstone of the progress of the country and the globe. And advanced material plays a vital role in shaping the future. Our journey through this program is not just an exploration of a scientific breakthroughs, it's a testament to human ingenuity, collaboration, and the relentless pursuit of knowledge. Today, I would like to highlight a few key aspects of why this field is so crucial and what we can expect to gain from our collective efforts over the next few days. Firstly, let us acknowledge that advanced materials are the building blocks of the modern era. They have infiltrated every facets of our life, from the gadgets used daily to the infrastructure that supports our societies. Our ability to create and manipulate the materials at the molecular and the atomic level opens up possibilities for enhancing the performance, durability, and functionality of this new material. One of the key aspect of this program is to delve into the recent developments that are pursuing the boundaries of what we thought was possible. Researchers and scientists around the globe are working on materials that are not only stronger and more resilient, but also possesses unique property that can revolutionize the industries. From self-healing materials to those with exceptional thermal conductivity, we are on the brink of transformative changes. Moreover, our discussion during this short-term program will not only resolve around the scientific aspects, but also with the practical applications of those uh, advanced materials related to the advanced materials. How can we integrate them into our everyday lives? How do they contribute to the sustainability of environmental conservation? These are questions that deserves our attention as we navigate the uncharted innovation. Collaboration in is the another key of this particular program, because such type of gatherings automatically will build up the network, not only local, it's global also. The interdisciplinary nature of the material science requires up to the breakdown silos and the works together across the various fields. Engineers, chemists, physicists, and experts from the diverse backgrounds must come together to unlock the full potential of advanced materials. This program provides a unique platform for such type of collaborations to reach the exchange the ideas and expertise the ideas amongst the expertise. As we engage in a lecture, workshop, and discussion over the next week, let us keep in mind that broader impact of our discoveries. The advancement we make here can contribute to solving global challenges ranging from the renewable energies to the healthcare. Right? In general, I encourage each of you to active participate, ask questions possible to the experts, and share your insights during this short-term program. Let us be inspired by the possibilities that advanced materials offers, and more importantly, let us collectively contribute to the ongoing narrative of innovation and the progress. Thank you, and wish you all a stimulating and productive experience during our exploration of recent development in advanced materials. Thanks organizers for giving me an opportunity to be a part of this inauguration session. Thank you. तिकडे ह्याला विचारा. Okay, thank you, madam, for a nice introduction. As a part of first session, I'm going to talk on the nanoscience and nanotechnology because as this is my first session, I thought it's better to give the overview about how the science is getting changed at the nano dimension, and because of that how the evolution is coming from the nanotechnology. I will start from the fundamentals and I will reach to the application. I will choose which where is responsible for to resolve certain issues where the common society is facing, that belongs to the sustainable materials, right? So thanks again for be part of the giving me a chance to be a first session. So if you are talking about the outline where I will cover in next 2 hours, that is introduction about the nanoscience and nanotechnology, how the chemistry, physics, and engineering is coming together to build up a novel materials, and then because of this, why the why people are doing the materials science, while in a scope for the materials optimization, how the nanotechnology becomes a key challenge. What are the key challenges and how the steps will be the uh, attempts to resolve the certain issues where the society is facing? Because at the end, impact of research, impact of material, impact of your work is totally depends on the how it is important, how it is resolve the certain issues of the society, right? So finally, I will conclude with the putting some collective challenges of the material science in front of you. Hope the slides are changing. I am on a third slide. I'll be more happy if somebody is just informing me if something is not moving, or what I am talking and what you are seeing is not matching. Okay. So the word is flourished by the statement by the Nobel laureate who got a Nobel Prize in 1996, Professor Richard Smalley. What he thought, what he talked about the nanotechnology holds the answer to the extent there are answers to be most of our pressing materials which needs in energy, health, communication, transportation, food, and water, which are the primary needs of the common people, right? So because of this we can say the advanced material is very important, which is we can say is a building block. The science and technology in the upcoming decades is a forecasted to be the revolutionized based on the knowledge of its ability to create, measure, manipulate, and organize matter at the nanoscale, which is 1 to 100 billions of the meter, which is expected to have a major implications for the health, peace, widely known as the nanotechnology. Because the science is getting changed at the lower dimension, people are manipulating, and the revolution is coming because the instrumentation is grown like anything, and we are reached to the level where we can see even a single atom, right? If you are able to see, of course we have the wider scope to manipulate, organize it as we want. You are seeing the growth of this field in electronics. The day by day the electronic circuits become smaller and smaller. We are saving huge amount of raw material. At the other side, we are accumulate a large number of electronic circuit in a small space. So because of that, data storage or the smaller electronic circuits, smaller becomes more efficient and all these things. So you are seeing the huge growth in electronic side, the because of the development in a novel materials, advanced material can say. So once upon a time, the story was entirely different, and it's at the other end of the what we are thinking about it. So earlier, big things are very good to see. This becomes the tourist places. Like see the great wall, the safety wall of the China, around 6,700 kilometers from east to west of the China. Other side, I mean, like a pyramid, big pyramids, having the uh, length maybe in 7 meter and measure into the 7 to 30 meter long. It's inside covering an area of like 53,000 meters square. It's big, huge pyramids were there. But now we shifted from the big to the very small, possible small. In a present time, the smaller is become a better. The reason behind this is solid state electronics says since it starts in 1957, it's been a shrinking. Today, the state of the art chip as a future future size of the 130 nanometers. But this is like a 10 years back. Now we can manipulate even a single atom. There are the microscope where we are observing the one heteroatom in a material, right? So this uh, gives the huge idea about how the materials are important as far as the uh, its implementation has concerned. I'm seeing some fluctuation in internet, so I thought it's better to switch off the video. So if you are talking about the molecular cell and its correlation with the complexity, as we know as a science people, it's difficult to model the picture at if the more than one atoms together or more than one electrons together also. Even Schrodinger has proposed the equation or the solution for the single electron, like a single particle in a box. So just visualize if the atoms are having the more than one electron, if the material is a cluster is having more than one atom, right? If the bunch of the cluster become a solid or the macromolecules, so the complexity will get increased if you move from this individual single simplest atom like hydrogen to the molecules to the cluster to the macromolecules to the solid, right? But this complexity we can minimize by making a small possible domains which are independent from each other. That we can do. Try to make the smaller possible electronic circuits, right? These are the possible things we can do. So this complexity is we can minimize if you go toward the lower dimension. So let me clear before enter into the subject. So what is meant by nano and how we can correlate with the length scale, right? So 1 nanometer is thus a 1 billionth of a meter or 1 millionth of a millimeter. It can be expressed as 10 to the power minus 9 meter and is noted as the nanometer. If you are comparing with the radius of one atom of a gold, it is a 0.14 nanometer. If you 1 nanometer means like a 6-7 atoms together will become a cluster having the dimension like 1 nanometer. Half a nanometer is the linear dimension of a small molecule, like a methane. One human here is around 100,000 times bigger than the nanometer. See, yeah, to see the nanoparticle, to see the material in a nano dimension, we need a microscope because beyond the limit of our here, we cannot see properly. Right? Because human hair is having some like 700, 800 micron size. So beyond this, we cannot see. So then another Richard Small, these two Richards has contributed a lot for the technology. Just understand first. What Richard Feynman said, Richard Smalley said, nanotechnology holds the answer for the certain means like a solution where the primary needs of the common people will get from that. What Richard Feynman said, there is a plenty of rooms at the bottom. In his talk, he has given the idea that yes, we can give the solution that there are plenty of rooms at the bottom. It means there are independent domains of the atoms, molecules together, which build up the material, right? And this becomes the foundation of the nanoscience and nanotechnology. And initiated in 1959 in the annual meeting of American physics, what means the APS, Calicut, right? So then, where the role of chemistry and physics? Why to develop a new material? That's the question will come to you. Because the new material means new arrangement. New arrangement where, of course, will be change the properties of that material. And the change in property we can use for a certain application, where the chemistry is about the making a new forms of material that have never existing before. Because if 10 atoms together, instead of 10, if you keep the 9 together, the properties are different. Instead of 9, if you keep 8 together, the properties are different, right? So this means, it means its new material is stand on 2 legs where the chemistry is involved. One leg belongs to the development of new material, that is we are curious about this, and further its growth is depends on the how this material is going to utilize for a certain application, right? So then the question comes, how the size matters. If you are talking about the size, if you develop one material at the nano dimension, like a 2 to 4, like a gold nanometer, like 100 to 100 atoms together, like a 4 to 5 nanometer particles, where we can see this gold is in a liquid form. 1 to 2 nanometer, this is the example of this. If you are talking about the particle size and melting point, below 5 nanometer particles, the gold is in a liquid form. See the melting point this side and this side. So this is the case actually. This is the beauty of nanotechnology, you can say. If you are able to maintain the size in a lower dimension, metals can go to the means like a solid can go to the liquid, metal can go to the semiconductor. So how it is, I will tell you in detail in next slide. But see the band gap versus the diameter. If the smaller the particle, like a below 2 nanometer, the band gap is like a 4 to 5, 3.5 to 4. And it comes, if the diameter is 10 nanometer, band gap is below 2, it comes in under the like a metallic form. It means what? If you 10 to 2 nanometer, if you shift, the material becomes metal to semiconductor. If you beyond this, like 1 nanometer, it will looks like an insulator. If it's single atom, it's difficult to take the electron from that metal. So this will be the case where the normal material, it looks like a platinum, gold, even aluminum, iron. These are the conducting materials that we are familiar with this. But because of the lower dimension, this becomes a semiconductor, right? And this semiconductor means like industries are growing like anything, because we are able to control the electron transfer in a material. That's the great evolution in electronic industries, we can say. The reason behind this is, if you are using the electronic circuits which is connected to the battery, just imagine. And if earlier batteries, earlier equipment like a mobile of like a 10-15 years back, around like a 2005 to 2010, imagine the mobiles were big, electronic circuits were big. there is the possibility to drain the energy throughout the day, even though you are not use the mobile. But these days is not like that. We are able to make a small electronic circuit. Semiconducting materials are coming into this, even though they are the metals. So because of the low dimension, they show the semiconducting properties. So battery energy of the battery is getting saved. If you are not used, the battery will be like a 100 to it will shift to the 98. But earlier was not like that. It will reach to the 50 or below that. For this, credit goes to the advanced materials, how they are coming, right? So another important property of the material is the surface plasma, surface properties. The credit goes to the Michael Faraday, who talk about the how the size is having the correlation with the color. He has done the experiment in 1857. It's a very simple experiment. He made a series of solutions like a gold. First, where having the less gold ions, Au3 plus ions, and the fifth beaker is having the concentrated, or where the Au3 plus ions are more. And what he has done, he has added the sodium citrate into this, equal amount of sodium citrate in all 5 beakers, and he went for a tea and come back. He observed the shade of colors in a solution. Trisodium citrate will act as a reducing agent, will reduce the Au3 plus to Au0 ions to the atoms. The cluster, the atoms which is present in a where in a first beaker, where the number of ions are less, atoms will be less. Atoms are distributed in a solution like far away from each other. They will not aggregate, right? Compared to this, if you are talking about the last beaker, that beaker fifth, where the atoms are more, they are nearby, they will aggregate, because every atoms, once ion convert to the atoms, see, I will having the huge surface energy, surface tension. So that will try to aggregate with another neighbor. So because of that, cluster will grow, and that growth will be more if the availability of atoms are more. So in fifth beaker, that possibility is more. So the cluster formation in fifth beaker is bigger than the smaller in a first beaker. So automatically, what he observed, first beaker is having the color which is entirely different than this. So the question comes from where the color comes. If the atoms comes together, they will share their atomic orbital and will become electrons become the comes on the surface as in the molecular orbital. It means the nanoparticles are having like this. Inner core is the atoms together, and surface will be full of electrons. The atoms are having the hold on the electrons. So it means it becomes the cluster of the ionic cluster inside and the electronic cluster outside. So the combined role of the ions atoms having the hold on the electrons will be the combined. So it means bunch of electrons will have on the surface and bunch of atoms in the cluster. The size depends on the how many atoms as participating in that particles. If such type of cluster come in a contact with the electromagnetic radiations, what happens? The electrons oscillate on the surface. The electromagnetic radiations is nothing but the magnetic field and electric fields together, which are acting perpendicular to each other. So it means like a waveform. Positive and negative ends are there. So such type of dipole, if it is interacting with the cluster, that oscillates, right? So their oscillation will be like this. Electron cloud sometimes interact with this one and will go away, then come back. So like this, right? As a result of that, what you will observe, if the particles are smaller, the electron hold will be stronger, requires more energy to them go away, like to resonate, to oscillate. So this is the actual idea for the to show the size dependent optical properties. Size dependent optical properties, and this is good to see for the materials which are having the size dependent properties, right? So same thing we can see for the materials which are having the frequency changes with the size. Slides are not moving, but just I join on another instrument, so where I am seeing the slide is not moving. We are on a 6th slide, but now I am on slide number 14, 13. Just let me miss, somebody should just help me to see the, okay, just I will manage myself, no issue. Okay, so we were talking about the frequency change with size, shape, local and surrounding dielectric medium, interparticle coupling. If the size decide the properties, so then automatically you can say the properties are variable with the, will oscillate with the electromagnetic radiations too. So if you are talking about the, if this decides, if the size and shape decides the optical properties, so then this surface plasmon resonance will vary with the dielectric properties of the environment, size of the nanoparticle, morphology of the nanoparticle, coupling between the nanoparticles also. If the environmental effect, if you are seeing, the gold nanoparticles are having such type of environment. If it is in a first it is in a glass deposited on a silica, so it is like a restricted platform, we can say. Dark blue spheres like a 50 to 90 nanometer hexagons, and red are the triangles which we have seen. If you are in a oil, is having the different, because the interaction of this oil with the nanoparticle will decide the absorbance. If you remove the oil, will have the different frequency of absorbance. So right, so this variation you will observe in case of the environment effect, right? If we have the core cell type of nanoparticles, if the core is something different and the cell is something different, see the black spot is belongs to the metal, and the little bit gray shade that corresponds to the some other material. That material may be like we have the carbon material or something else, right? So this interaction also decide the properties. If we are talking about the shape, see, if you have the rod, there are two types. If the surface electrons are having the interaction with the core atoms, and the core atoms and that the positive core and negative portion of the electrons, if this interact with the electromagnetic oscillation is proportional to the length of that rod or the wire, right? That decides. That we used to say it's the aspect ratio, length by width. If you are talking about, it is in a several kilometer. If the nanowire is there, if it is in a kilometer range, it's having the different color. That comes from the variation because of the length, and the width will be same. The signal is here because of the length. The variation is there, so it looks like a mixed color. If there are two observances, it represent the optical means like a mixing of two colors together, right? So this variation we can represent the system's response in terms of the mixed color, right? So other shapes are like if the multi dimensions are comes together, the discrete dipole approximation represents the mixed variations in a color, right? So the chemical properties also varies directly having the association with the surface atoms. So it means what? If you have the small, get small becomes more benefits, and of course, it is a small number of atoms will come on the surface, and surface becomes more active, right? So likewise, we have the plasmonic properties, information transfer in a nanometer range scale from one cluster to the another cluster, and this will help us to propagate the light in a few nanometer. It means somewhere we have given the light, it will transfer to the dark if you have the connection with the cluster from one side. So from here you can give the signal, and signal will reach to this side from this side, right? Those This is possible. This field is a new field, and it is upcoming field where the new materials are coming, which show us the plasmonic properties. Another beauty of these nanoparticles is the amplification. People are using like a colored compound to, like a Dopplers, or like if you have the X-ray, we used to add the cobalt clusters. So, but cobalt sulfate or something like that to get the bright image, to find out where the fracture is there, right? So, but and some other optical centers like a dye molecule people were used to use. But instead of that, if you are using the nanoparticles, is having the huge uh, amplification properties, so that help us to see the for the diagnosis purposes. Where biomedical applications are more, that we will see afterwards, like in detail. But if you are talking about the beauty comes from the nature. So why the materials is having the color? Because we have the capability to, as the material science people, we have the strength to organize the atoms as we want, right? So this has come from the nature. So here we are not in the dye shade. This shade is coming because of the difference in organization of the molecules. The peacock is having the shades in a color because the molecules, the organized molecules are having the different. This is actual the God's own nanomaterial. Having the absorbance at the higher energy, lower wavelength. Particle electrons are away from the positive center, requires low energy to take the inflation on the surface, right? So this oscillation requires lower energy. So experimental data, right? Another important property used to say is the band structure or the energy diagram, we can say. Very simplest, from simplest way, if you are talking about at the very fundamental, if you two atoms comes together, will become a molecule. So chemistry behind to become a molecule is two atoms share their atomic orbital, which is energetically same or the nearly same. So that atomic orbital will convert into the molecular orbital after the mixing and recasting of the atomic orbital. And the molecular orbital is having the particular strength where one will go down and one will go up. The down one will be the HOMO, upper one will be the LUMO, that we used to say. So this gap between this HOMO LUMO, after connecting with the more than one atoms, like two more atoms, if you introduce two more atomic orbital will get participate, and two more molecular orbital will get formed. So this will be like if the few number of atoms comes together, we used to say it's a nanoparticle or the nanocluster. So in that case, we have the few number of atomic orbitals, molecular orbital, which has the HOMO, we used to say as the valence band, and the collection of the LUMO that we used to say as the connection band. So the gap in this HOMO and LUMO will be the the band gap in this case. But so likewise, the growth will be there if the more number of atoms together will be the band gap is small, and one stage will come, there will not be the gap between the valence and conduction. It is like a bulk solid. So self-assembly of number of atoms or the molecules together, the discrete intervals of atomic orbital merge into the energy bands, that is either valence band or the conduction band. So this is the just pictorial of how the bonding happens and how the antibonding happens and how the discrete energy levels, density of state creates at the nanoscale, which is proportional to the number of atoms. Right? So this is the concept of the atoms, molecules, discrete energy levels where the quantum dots we can say, and further we have the bulk solid state. This is the actual band gap where we have we are reading from the textbooks. Especially if you are talking about the gold as an example. So if the gold atoms like a gap like 1.8 volt energy will require, and the gap is like 1.5 energy volt, electron volt. So this much gap, if instead of 13, if it is gold 38, 1.2 volt, 0.9 electron volt gap is there. So by this way, if we have the gold 225, so it further that becomes a gold. The cluster, its work has like a molecule like energy gap. It is like a metal like a quantized charging gap, and this side we have the bulk gold. So to potentials of the electrochemical charge. So it means what I have to say here, if you have the smaller nanoparticle, will work as like a molecule, like a cluster, right? So then another property, if you are talking about, we have surface to volume ratio. If it is increases upon the decreasing the size of the gold nanoparticle, the properties of the surface atoms increases where the smaller part. If the smaller part, making small means what? Taking out the atoms which are inside and we give them the exposure. As like a stone. If we have the stone, break it, break it, break it, break it. At the end, you will get the cement from the stone. Cement is having the different property than the stone. We cannot hold one bricks by another bricks by using a stone, right? But same stone, if it is and their interactions holds two different bricks as a cement. So this is the actual strength if you go toward the lower dimension. At the lower dimension means we are giving the access to the atoms which was there inside. See, compare this 3 nanometer with the 30 nanometer. Huge number of atoms are inside. The skin of this cluster is only about 5%. And here, skin of this cluster whose size is 3 nanometer, like almost 50% atoms contribute in a skin. So this is very important. Most of the cases where the catalysis, electrocatalysis, the electrodes, batteries, supercapacitor, or some other like sensors, everywhere, the atoms on the surface of the material is very important. Right? So that decide the performance. Not only because see the another side, if you are saying the surface atoms are more active. The reason behind this is there are some bonds which are empty bonds. There are some accessible sites are available. Some coordinations are open for the interaction. So in that case, the reactant comes and interact with that sites and will get converted into the product. So such type of things are there. If you are going to the lower size in terms of the nanomaterials, so the such type of active sites are more accessible sites are there. And one atom with a more number of active sites means automatically that atoms exceptionally behaves more active. Right? That is the optimization people are doing in case of the nanomaterials. So this is an example of how the electrode potential changes with the size of the cluster and some other conjugation we can say. So then question comes, how to make these nanoparticles? You are familiar with this? I was talking about the example of the cement from the stone that comes from the top down approach. Here, see, this cartoon itself gives the idea. He's breaking the material and making the smaller pieces, as like making a atta from the wheat, from jawar. These are the examples of the top down, where we can break the materials to the micron or to the nano. Another side where the chemistry involved, more chemistry is involved, where assembly of atoms together to make the particles, to make the clusters. Especially in this case, we have the control because the atoms are in your hand. If you are not giving the input, nothing will be the form. The product will not be there. So this beauty will help us to get the clusters in a controlled manner. These are the examples I am talking about. So if you are talking about the bottom-up approach, it is nothing but a self-assembly of atoms or the molecules together. We have these different method, like a chemical method, chemical vapor deposition method, electrochemical method, where they can do the electro deposition in a pores by making the polymer means like a porous alumina, anodic alumina membrane. And another is like a galvanic approach. You give the access to the substrate to interact with the ions present in a solution. There will be the exchange. Some ions will get deposit by via the reduction, and some will be like oxidized, will come in a solution. Like, so this is based on the electrochemical potentials. Some chemical means like a controlled low concentration gradient and use the some mild reducing agent, will get the controlled nanoparticles, right? So chemical vapor deposition approach is there, like a vapor phase controlled synthesis of nanomaterials. And another approach is like a top down, where we can make the nano clusters, nanostructures span the macro structure. But unfortunately, we cannot get the homogeneous particle distribution, will be like more. As we know, even at home, we used to use the mesh to take it the bigger clusters from the our wheat powder, right? So this is the case actual, the problem of top down. Here we don't know how many times the hampers that particle comes in under hamper, right? So this is the actual, the basic difference between the top down and bottom up. But most of the people, more the people are working on the bottom up method. But top down method is commercially viable. We can do it at large scale. Industrial scale people are working on the top down, where the physics is involved more, engineering is more. This is simple example I have talking about the gold nanoparticle, how it is formed. So I don't want to go in more detail, because system to system need based synthetic methods are coming up, right? So how the growth is there, one atom, once the atom formed from the ion by the reduction, so atoms comes together and minimize their surface energy, right? So there will be the competition between the atoms to atom interaction and atoms to molecule interaction. One stage will come, atom atom interaction becomes weaker with the number of atoms, and all of a sudden all molecules comes together and will protect its surface. So this is the case how the nanoparticles will get formed. So this is the way how this is the gold nanoparticle is covered by the organic molecules, like a protection, surface protection, like a surfactant, we can say. And because of that, this will not be allowed the atoms to go out or some other atoms to take it emergency in. So these possibilities are not there, because there is no opening at anywhere. The compactly packed organic molecules are there on the surface, right? So this material we can characterize. There are n number of characterized techniques. We know the inorganic material is characterized by the X-ray diffraction, UV visible, electron diffraction, X-ray photoelectron spectroscopy is there. How many how much inorganic content is there in that cluster, that we can do by the thermogrammetric analysis. Morphological information will come from the transmission electron microscopy, plus spectroscopic information we can get from the atomic force microscope, scanning tunneling microscope. And organic clusters, organic component we can characterize by the n number of spectroscopic techniques like FTIR, NMR, Raman is there. X-ray photoelectron spectroscopies, of course, will help us. Thermogrammetric and DSA, differential scanning calorimetry. This will give us the idea about the holding of this molecules, holding by the molecules on the inorganic cluster, right? So then we can turn toward the size-dependent catalytic, optical, electronic, magnetic properties of the materials, right? So this nano architecture, superlatives, novel properties will be the corrective interactions of this material, right? So this is a transmission electron microscope. Just I'm showing for your information. So then, if you are talking about the gold as an material, because it's very biomedical, means like a biocompatible, you can say. The reason behind this is it's having the side, is like because of this strength of the gold is biocompatible activity. It's used in a bioimaging, biodiagnosis, and as an also for the therapy platforms where the gold is a good reason because of this in vivo, in vitro delivery, biodelivery, this gold is used. Why is gold? Because it's highly biocompatible and is non as cytotoxic material, stable in physiological environment, is facile manipulation of their surfaces either by the thiol group or the amine group. Optical properties are tunable and very sensitive for this. Specific optical properties, especially we are talking about the surface plasmon resonance, which will be there. So as to get the image, it's where to get the contrast agent, gold nanoparticles people are introducing to get a better image, because each nanoparticle will act as an amplifier and will like a soldiers are standing around the tumor with the batteries, like that image will come, right? So problems for the selective labeling of the protein, direct absorption of the protein onto the gold nanoparticle, but protein denaturization may occur, sulfur-sulfur bonding, lose its activity and selectivity necessity to control their bioconjugation, right? So this is one case. So if you are talking about the imaging, load the antibodies on the nanoparticle surface is the first step, and allow them to interact with the antigens which are belongs to that tumor. So this in vivo imaging we can get it. So because of this interaction, the surface property changes and the interaction with the electromagnetic radiation vary and will get the signal. So you see the difference. If you have not added the nanoparticle, will be like this. And if you have added the nanoparticle, this portion will be more, what you can say, the brighter. Will get the information that this is the place where the tumor, and that will help us to get the targeted, what you can say, the image, this operation of this particular tumor, you can say. Another application of this gold nanoparticle is to get the binding of, is like a detection and identification of DNA strand, conjugation and color. If it is a nanoparticle and if the strand is free, if the strand interact with this, so additional interaction will be responsible for change in the color of that solution. This is about the optical properties which you have experimental data I am showing here. So this help us to as the biosensor or characterization easy to implementation. No radioactive or fluorescent organic probes are there. If we are talking about the therapy, photothermal destruction of the tumor cell, where IR exposure to the cell will help us to get the ablation of the tumor cells via local heating. So if you have the nanoparticle, will capture the radiations and will emit in the form of the IR radiations to this. So this energy is more enough to kill the tumor cells by using the photothermal destruction. So this is one of the approach we can say, right? So this is based on again the size of the nanoparticles. So this medical benefits from the heat is shown here. So if you expose with the gold nanoparticle IR exposure, see the tumor cells has got damage, means like destructed. So this is the case that will sometimes help us to avoid the radiotherapy. This is big, actually the big problem people are facing with the cancerous student, means cancerous patients are facing actually. In conclusion, gold clusters for the biomedical applications are because of their biocompatible, easy to elaborate with the functionalize with the molecules, easy to detect. A large number of detection techniques are there, easy for the functionalize to target the agent associated with the diagnostic and therapy. Right. So another, I will move to the the specific bunch of nanoparticles, especially which are the from the carbon family. Question comes, why the carbon is having the extraordinary importance in the materials, advanced material. The reason behind this is the carbon is having the more complex in tendency. Its covalently bonded structures are huge. Is having the catenation power, we can say. Before 1980, there were only two allotropic forms were visible for us, it's known for us, that are the graphite and diamond. But after that, you observed C60 has come. Richard Richard Smalley has discovered, and he got a Nobel Prize on that. That is C60. 60 says the number of carbons involved in that ball, buckyball, people used to say. Then on the way, C70 has come, little elongated form of C60, and if it is elongated on a large scale, CNT has observed. Izima is a Japanese scientist. He was not a scientist, but he was a microscopist. He observed the hair-like structures and which are having the hollow center. So that is carbon nanotubes. If you cut the carbon nanotube very systematically, it opens and will have the graphene seeds. Right, and these graphenes, you will see the graphenes are like seeds. If you roll, will get carbon nanotube. If it is open, will get the what you can say seed from this. So this type of carbon material we can use for to make the mimic the lotus leaf and the self-cleaning material people are made by the carbons, right? So this lotus leaf is the natural gift, you can say. So people are modifying the surface, tuning the surface to get the self-cleaning material. Like if you use the material like made by the silica as a shirt, just spray the water, the dust will get clean. Windows are coming like this, self-cleaning windows. So another important property which we observed, while the materials are helping us to change the properties at the lower dimension, that comes from the core, that property is the magnetic property. As we know, as per our knowledge, the magnetic properties comes from the magnetic moment of the electrons. We have the nucleus, and around the nucleus, electrons are revolving in their orbit. So that orbit is having the orbital motion because it's around the centralized to the nucleus and is moving around. During moving around, these electrons are having their own spinning too. So just visualize, one atom is there and around it another electron is revolving. During the revolving around the nucleus, is having the center of force toward the nucleus, and another one is the amongst their own body. So it is having two different motions. One is orbital motion, another is the spin motion. Each has a magnetic moment, right? Just imagine if such type of atom is locked with some other atoms through the bonding. If the bonding is there, automatically this electron becomes restricted. There is no scope for that electrons to revolve around because if some other nucleus comes here, so these electrons will not, this nucleus will not allow electrons to go this side, right? So this problem is there. And also, if once this electron is locked with the another electron, there is no scope for electrons to spin also. So because of this, the magnetic property hampers, right? So this is the examples I am talking about. I don't want to go in more detail, but you are familiar with this. So if you have the array of the atoms together in a solid, the magnetic properties will have the bunch of domains together, right? So see, from here to here, if you are getting, we have the magnetic domain which is independent, we can say. Here we have the dependent domains, the n number of n, and south and north poles are there. So the if you have increased the domains and domain size or the walls, we can say the grain boundary and grain size, same thing. So the properties will be more. So it is like this. The if you are expecting the more nanomagnetism is there, so if you go to the lower dimension, we have the performance is more. So how to make it? Take the bulk system, try to make it. If it is a bigger, the few atoms comes on the surface. If it is a smaller, all atoms comes on the surface. So like this, smaller the domain, that will act as a single domain, will perform extraordinary. So in this case, if it is the smaller nanoparticles, we have the more performance of this, and use we can say the huge data we can store. If you are talking about the data storage material, I'm showing here the CD. So this is nothing but domains like a magnetization and positive and negative magnetization domains are there that are systematically distributed, will act as the storage bit cells, single domain magnetic islands. So this 1010 data storage bits will help us to store the more data. If you make such type of smaller domains more, possibility to get the more data storage is there. So just see the pen drives to see it looks same, like one is 16 GB, one 80 GB, and one is 120 GB. That pen drives are same, but the labels you will see the difference. But inside material where the smaller domains are different, right? So this possibility will help us to store the more data, right? This is about the magnetic properties. We'll come to the another applications of the nanoparticles where huge importance are coming, where the energy is a global problem. Is not only India is facing. Yesterday itself we saw some humors that the people are going on a strike. So the all petrol pumps will get closed. There was a huge queue, right? So it means we have the dependency. We don't have the renewable resources with us. We have dependency on the petrol diesels, petrol pumps. They have the dependency on the resources which are controlled by the outsiders. We don't have the enough energy resource as far as the energy has concerned. And so that actual the growth of the countries depends on their own energy resources are not, or are there or not. United States are having the global hold. Reason being, this is they are independent for this. There are still their resources are stored. So this is, but in other side, if you are talking about this, energy is having close connection with the environment, because we know the burning of petrol and diesel result in the carbon dioxide, and the carbon dioxide in the environment will kill the what you can say the routine of the seasons and all these things. And pollution is another issue. So energy becomes one of the grand challenge of our time. Energy is not a monolithic issue. It depends on the supply, demand, conversion, application, scale up, location, geographical location, independence, means the international government policies, environment, climate change, GDP, of course, the carbon intensity, infrastructure, technology transfer, policies, government policies, their sustainability, and of course the public acceptance. Still, we don't have the acceptance from the public for the LPG gas. In villages, people are again worried: is the gas we have systematically made it off or on as such? So these are the issues. So the fossil fuels will be important throughout this country. Renewables are growing rapidly, but they are not enough. Like you are seeing, the government is giving the subsidy for the solars. Government is giving the subsidies for the wind fans. So, but the will not be sufficient. Efficiency or the conversion is not that much which we are getting. It means what? We don't have the alternative for the fossil fuels. We are totally depends on this, but awareness should be there. So you see the how the fossil fuel is dangerous. You might have seen on the your what you can say, the ticket. Which ticket? The aeroplane ticket. At the bottom there is a line from for per seat, means for means you are moving from the Pune to the Delhi. This much carbon dioxide because of your this journey is emitted in the environment. This much ton, this much pound. So like this. So this means per seat how much consumption is there, they have calculated. So, but we don't have the alternative. You might have seen the picture on the cigarette pocket also, but people are not avoiding. The reason behind this like this only. Especially if you are talking about the transportation or the growth, the energy consumption is closely correlated with this, because energy consumption will come from the transportation, will come from the industrialization, will come from the lifestyle. All three are necessary for to compete with the well-developed countries. We cannot avoid the transportation because growth decides. We cannot avoid the communication because that growth decides. We cannot avoid the industrialization because this growth. This closely connected to the growth of that country. Unfortunately, all countries were stopped during the COVID. That's why our growth is not visible. Our lock is not visible. Right? Because everybody was stopped. But just visualize, COVID was just only in India and no other countries, all countries were growing. Just imagine, we will be like thrown back like 100 years. Our economic will be like a down. So this is the difference is there. So why this problem is more visible now? The reason behind this is the people are wanted to grow like more, and the globally, if you are talking about the huge use of these energy resources, result into the carbon dioxide in the environment, and that result into the global warming, and both ends of the galaxies are like burning. And so you might have seen somewhere, you might have read somewhere, one day the this earth will get down to the water. The reason behind this is the sea level means like because of this, ice melting is more nowadays, and the 70% water is become shifted to the 80%, 90%. One day will come like 100% water. Right now we are in a 70, 75. So this is growing. The water level is going up, and one day will come. So unfortunately, we are in a zone where the dry area is there, and unfortunately, dry becomes more dry if the temperature grows. And the carbon dioxide is the dangerous reason behind this is it makes the layer on the surface in such a way that the radiation which are coming from the sunlight that should hit the surface and go back, but unfortunately, this becomes engaged on the surface. And because of this, the heat surface become heat multiple times, hampering on the surface, result into the surface becomes hot. The evaporation will be there. So dry area becomes dry, and the sea level becomes more evaporation, the vapor pressure increases, and because of this unequal pressure, so these vapors of water will sip to the earth level, and nearby places to the sea level will get heavy rain, like a Chennai flood, Tamil Nadu, multiple places. Mumbai is facing a routine problem, right? So these are the problems which we are visible. Another problem with the carbon dioxide is nowadays, the recent studies about the carbon dioxide says carbon dioxide, every species we know the gravitational force acts. Gravitational force acts which is proportional to the mass of that species. Carbon dioxide is having the mass which is coming from the two oxygen and one carbon, right? That is m into g. So that keeps carbon dioxide stable at 5 to 7 feet from the earth's surface. Just imagine in metro cities, the global abundance, natural abundance of carbon dioxide is below 1%. But in a metro cities like a Aurangabad, like a Pune, like a Mumbai, this carbon dioxide level is growing up like anything, like 80, 85. Just imagine in the zone like a 5 to 7 feet, the carbon dioxide content is like 80%. What about the oxygen? Which this carbon dioxide displaces the oxygen in that zone. So that creates the problem. We will feel the uneasy. The clouded areas like a bus stop, like a railway station, like an industrial zone where the carbon emission is there. So these places becomes a danger. So that creates the problem, like will feel the uncomfortable for the breathing, not because of the pollution, because of the carbon dioxide. So this is, it means we used to say carbon dioxide is good for the health, or this not harm for the health, but indirectly this is becoming overdose of the carbon dioxide is becoming a pollutant, right? We know the definition of pollution. I don't want to go in more detail for that, but this is the issue which we are talking about, and this comes from the lifestyle. See the scenario, earlier scenario, like a 30 35 years back, so the use was not there, but now see, everybody wants to be carry the vehicle, two-wheeler, either two-wheeler or the four-wheeler. They wanted to move from the like two-wheeler to four-wheeler, four-wheeler to the aeroplane, right? So a huge amount of use is result into the emission. There are resources people are developing, but unfortunately other side is not secure. We don't have the control on the end users. The population is growing like anything, right? So this is the case about this is about the Mumbai, this Delhi, this Calcutta, right? So there are some same scenario is there in other countries like in China, right? So because of this imbalance, the accidental rain comes. We know the example of a Chennai flood. So how the people are suffering? It took like 2 to 3 months to recover from this disaster. Thanks goes to COVID during these 2 3 years. Little we recover the, but this is not a way. Other side was completely blank, right? So, but it's a very eye-opening issue, which you can say, especially if you're talking about the India, we on a top where we have the mega cities. This is the data of 2015, like a 7 year back, 7 8 year back. We were on the top with the mega cities, and these mega cities are like increasing nowadays. Again, few more cities has entered. Earlier, Pune was not a mega city. Mumbai was there. Mumbai, Bangalore, Calcutta, Delhi was the limited cities were in mega cities. But now Pune is entered, Hyderabad is entered, uh, Cochin is entered. This side, Guwahati is entered, right? So the mega cities are growing, entered in more. The reason behind this is people are moving from villages to the cities. Sometime next few years are there, Aurangabad will get entered into this. And because of this, what happens will come in a red zone. No other places like cloudy places we are finding like India, right? So this unfortunately kick us into the red zone instead of a green zone. See, the United States people are very happy. They are having the pollution quality index is in a green zone, right? So that's the reason why those who enter, those who we went out, they don't want to come back. Even though they come back, they will not be the compatible with these problems in India, right? So these are the serious issues we can say. So yes, there is an alternative as a renewable energy, nuclear power is there, but unfortunately, people are not accepting this. Even though, see, a few years back, Jaitapur was the plan from the government side, but local people have opposed this to install there. So there are more than 100 nuclear submarines are there, 450 commercial nuclear reactors are there. So the most of the places, uh, the percentage wise, the nuclear power energy are using. The reason behind this is small amount of input. If you are given the output, huge amount of energy you can get it from them, right? So the United States around 20% and 17% from the India itself is taking the energy from the nuclear powers. But unfortunately, the handling is very important. 2011 crisis at the Fukushima was there because of the earthquake, the power cut, and the cooling system they are not able to manage. So there was the blast. And nuclear pollution is dangerous than any other pollutions, right? So energy resources are there. The non-renewables are like coal, natural gas, petroleum, nuclear energy. There is no alternative for this. Alternate energy sources are there: wind energy, solar energy, oceanic energy, hydropower, geothermal, biomass. But uh, their output is very less. We need to be depends on the energy which is coming from the sun and the fossils, right? So there are people are developing a different energy resources. Hydrogen economy is very important. Fuel cells, lithium batteries, supercapacitor, solar energy storage. These are the growing areas of energy conversion, energy storage. Synthetic trees, where the carbon emission we can control. Synthetic trees means which help us to capture the carbon dioxide from the environment. Means the in the metro cities, the well developed hotels outside, they have arranged this such type of carbon capturing material in terms of the trees, right? So this is the example I'm talking about. You can where the fuel cell based cars are there, right? Nowadays this becomes common. Travels are coming with the carbon, where the um, uh, fuel cells are used, right? So if you are talking about the hybrid materials, where the nanotechnology helps, question comes: if you are talking about the renewable resources, energy conversion, so then where the nanotechnology enters? If you are talking about the solar cells, energy conversion, so the photons can free from the electrons is very important. So where the semiconducting, and as we know, by making a layered material at a nanoscale, or by making a nano clusters, we can make the electrons free from the cluster, so which generates the electric current. So the photon energy will be help us to convert these to electrical energy, right? So the chemical reaction, and there is a chemical reaction at the atomic level in a batteries or fuel cell, which regenerates the electrons and the ions, which are responsible for the charging and discharging mechanism. Right. So that again come back to the words by the Richard Smalley, where the nanotechnology help us. So then question comes: we are on the top. It's a great word by the Herman Kupier. He talk about that. So we are at the peak of the oil age. We don't want to use more, but that will be the beginning of the hydrogen age. Anything else is the interim solution. Uh, the transition will be very messy and will take many technological paths, but of course the future will be the hydrogen fuel cell, right? So here onwards, we need to think about the protection of the environment. Instead of hydrocarbon burning, better to go for the hydrogen as the active component. This is the actual the summary of the story which here talked about. General Laurie Bruns, the director of the R&D General Motors, he talked about the General Motors absolutely sees the long-term future, yes, but of the world being based on the hydrogen economy. If it is hydrogen economy, so the possibility to carbon emission is zero, right? Then question comes, why hydrogen? The reason is that it's having the 38 energy density. It's huge, 38 kilowatt hour per kg. This much energy density you can get from the hydrogen, and this compared to other resources is very huge. And this hydrogen from one side and oxygen from other side, if you supply to the electrochemical system on particular materials, will get the energy that is electrical energy, and that is hydrogen stores approximately 2.6 times more energy per unit mass as a gasoline, right? Hydrogen primary sources are the like coal, natural gas, biomass, solar thermal, solar photovoltaic, hydrothermal, wind, nuclear energy. And this hydrogen we can collect from the material and we use for the different purposes, either for the transportation through the fuel cells or through the industry and for building for different purposes, and leading to the zero emission of the carbon dioxide, right? Then question comes, what are the resources or the hydrogen, from where the hydrogen is majorly produced? That is 48% hydrogen is taking from the natural gases, 30% people are collecting, that is from the oil, 18% that is from the coal, and very 4%, very less, from the electrolysis of the water, right? So this where we have the scope. How the scope comes? Because water is naturally global abundance, that is more than 78%. This is one case. Another case is use the solar energy to split the water, and will get the huge amount of energy from this, right? So this is another way. So the photo plus electro, if you combine together, will get the better performance as per as the hydrogen production from the water. Each molecule of water will give the one water hydrogen molecule and half oxygen molecule, right? So this is the beauty of the water electrolysis. So then we thought to work on the water electrolysis, right? So the what is mean by this? We have the anode, we have the cathode. Anodic reaction is corresponding to the oxidation. Oxidation of what? Oxidation of OH minus from the solution result into molecular oxygen formation. Other side is the reduction, which is the cathodic reaction. We have the H plus present in a solution that moves toward the cathode and result into H plus into the hydrogen conversion. And once, and another beauty of this system is that this is like a fine, means like a complete partition. There is no oxygen in will come in a hydrogen zone, or there is no hydrogen which will come in a oxygen zone. So right, this is the actual beauty of this proposed system, where we get the better response, right? So this is the example I am talking about. But there are certain barriers. The barriers are not only for this hydrogen oxygen production, these barriers for all possible electrochemical system, especially we have seen observed in case of the batteries. Life of the battery is half than the life of your electronic circuit. That's the reason why for the age of one mobile we need to change a battery twice. The reason behind this is the electrochemical interface, that is interface of the liquid solid with a liquid, and always that makes the electrode corrode. Yes, there are materials which are stable like a platinum, which is good, having the more stability. But we cannot use in a common electrochemical device. The reason being this is very expensive. Rhodium is more stable than the platinum, but that is again more expensive than the 3 times expensive than even platinum. So these problems creates the major issue. So then what people are doing, people are connecting this to the cheaper material. Platinum, ruthenium, platinum tin, platinum iron, such type of alloy systems are coming. Carbon-based systems are growing. Electron materials, and this because of that, what will happen? The electrochemical systems will slowly give the performance list. See the mobiles. Initially, if you if you have taken the new mobile, the performance is high. We don't need to charge in a day. But after 6 months, you will see at the end of the day, like at 6 o'clock, we need to keep on for some time on charging. After that, at the mid of the day, after a year, at the mid of the day, once you need to charge it. So this problem is there. So that electrode degradation, uncertainty in their lifetime, high ohmic losses, low corrosion losses, these are the problems which are acting as the barrier for the commercialization of the electrochemical devices, especially maybe the battery, maybe the supercapacitor, maybe the even the hydrogen production workstations too. So this is there. So the people are working on to develop the new and new electrochemical systems where the materials are having the more importance. So that is the reason why the advanced materials becomes a creditable materials. Especially if you are talking about the hydrogen-based systems, carrying hydrogen, transportation of hydrogen is very difficult. The reason being this is not safer. Yes, there are some countries they have made their policies like that, but we cannot generalize here, especially for the India. If you are carrying a vehicle which is where we have filled the hydrogen instead of a diesel, it means like we are carrying like 100 bombs of hydrogen together. So this is not safer. Small external shock is more enough to blast it. And our roads are not good. We are not following policies of government policies of transportation, like traffic and all these things. So these are the issues where hampers the commercialization. Then people have shifted to the hydrocarbon based, but the carbon monoxide and oxygen are the internal ingredient, which are active ingredient. So that reacts irreversibly on the electrode surface, and some of the sides will get blocked. So that is the reason why the performance comes down. Another is the dispersion is the issue. As we know, self-cleaning is the good approach for electrodes to make them sustainable. So like platinum is, if the platinum is the main catalytic system and it corrode because of the irreversible binding of the strong acting ligand like a carbon monoxide, which is the intermediate species from the carbon means like a burning of the fuel. So to clean it, if you have the ruthenium nearby, this will be the sensitive for the OH. So the OH plus CO will get the carbon dioxide, and the carbon dioxide will come out, and the platinum will be fresh, ready for the next reaction. So this is to say is very good. The hypothetical saying is very good, but we cannot make the system like the ruthenium platinum chain. So this is the problem. The problem is the organization of the atoms in a cluster. So then people have shifted from to develop the material which is sensitive for the arrangement, like a efficient electrocatalytic system, which is systematically convert the fuel to the carbon dioxide instead of some other intermediate. Right. So likewise, there are the modifications. There are n number of catalytic system people have developed. I don't want to go in more detail, but the idea is to develop an advanced material for the production of the hydrogen. So this is the reaction, hydrogen evolution reaction, where the two electron transfer, the material which will help us to convert this into the hydrogen. There are 4 electron transfer oxygen generation molecule. So see, especially in case of the electrochemistry, we cannot play with the one electron. We need another electrode to do something. If you have concentrated on the oxygen generation, somewhere the hydrogen generation will be there automatically. If you are concentrated on the hydrogen generation, somewhere oxygen generation will be there. Right? So then people are developing a material which is good for the hydrogen generation, means water reduction. Some people are working on the material optimization, which is good for the oxygen generation or the oxygen or water oxidation. Or some materials are good for both. Either to develop the anode good, cathode automatically will support, or do the cathode good, anodical reaction automatically support, or do the development of both, will get the better response. Right? So by this way, the electrochemical reduction oxidation will happen on the water. So I'm giving even here the one example. We have developed the graphene. Graphene is further modified by the developing the pockets by the defects, and the defects will filled by the boron, that is systematic substitutional doping of the boron in the network of the graphene. That is boron substituted graphene we have seen, and that center becomes more active as the electron source for to produce the hydrogen from the water molecule. Right? So this is the case. Actually, I don't want to go in more detail. If you need details, you go to this article. Another system where accidentally we are able to make the nitrogen doped carbon nanotubes. We already idea was to develop the carbon nitride, which is doped with the cobalt, which just we have heated for the 700 degrees centigrade. We got the cobalt nucleated nitrogen doped carbon nanotube, and nitrogens are of two types, like a pyridinic and quaternary nitrogen. These two nitrogens are more active centers for to get the hydrogen production from this. There are some other cheaper material used like a cobalt, nickel to develop the system for the hydrogen and oxygen generation. In general, we used to say the water splitting reaction, and these materials are good compared to the more means like a reference system like a platinum. Herein we have developed a bimetallic system. It's like by functional system like a rhodium nanospheres decorated on graphene oxide, and we observed that system is this proposed system is better than even platinum. Right? Similar, I don't want to go in more detail, but some examples, some metal free system, because the metal, if you are decorated on carbon nanostructures, the leaching is the problem. We are playing with the acid, strong acid, strong base. The connection will get loose and the metal will come out from the system. So that by keeping that in a view in the mind, what we have done, we have decorated this with the molecules which are having the active centers. Like amino acids we have used systematically. One end we have coupled with the graphene, and another is kept open for the oxygen and hydrogen containing species to interact to show the performance. That is L-ascorbic acid, means like lysine modified graphene oxide we have synthesized here. Similar other systems are here. Tridiethylamine we have used here. Tyramine we have used for the modification, and we have seen some of better response from this. Another system where the multiple components together, like a cheaper material like a zinc, tin, sulfur together, we have modified the surface, and that we have used for the certain applications like HER, ODR. This bifunctional response has come, and this further coupled with the nanoparticle with the graphene, that with the amine functionalization. So multiple modification result into the further optimization. The response has come from this side to this side. So this type of material also can use for the fuel cell reaction, that I don't want to go in more detail, but see the surface smaller particle, their conjugation will help us to show the response more. Response we have counted in terms of the lower potential required to show the fuel oxidation reaction, and on the same material will get a high current density, will be the better system for the performance. Again, we have modified the carbon nanotube with rhodium nanostructures by making the pocket on this, and by the galvanic approach with the aluminum, we have exchanged this with the rhodium 3 plus ions because of the difference in the potentials. So we got a systematic decoration of the clusters of the nanoparticles on the surface of the carbon nanotubes. This temperature dependent structural evolution of the rhodium nanostructures, that also we can do by the chemical vapor deposition, and we observe the temperature dependent phase transitions, the growth of the nanoparticles in the what we can say, the asymmetric plane, that makes the more atoms in asymmetric plane will responsible for to show the conversion is in a better manner. So likewise, the cubes are having the restricted asymmetric atoms, and further with the temperature, the transformation is to go towards the stability, and this system is better for the electrochemical fuel cell reactions. Right. In another case, we have developed the nanospheres of carbon by using the mixture of the naphthalene and camphor together, and we used this for the carbon nanosphere formation. And this system is good for the metal free system for the ascorbic acid oxidation as the one of the fuel cell reaction. Right. Some other fuel cell reaction also we have done on the bismuth cobalt cluster, which is decorated on the graphene, and this system is good for the ethanol oxidation. Similarly, nickel based systems we have used for again the ethanol oxidation. Here we have used the silver decoration on the C60 Buckminster fullerene, and this system we have used for the hydrogen oxidation. Hydrogen is the another potential candidate, is where the we can use the where the hydrogen is reached. Generally, hydrocarbon like a methane we are using. If you instead of that, if you are using the hydrogen, nitrogen will come out. If you are using the fuel as a methane, carbon dioxide will come out. Nitrogen is not harm. We need a nitrogen. Actually, nitrogen fixation is the another approach of research where the fertility can improve, the soil fertility can improve by the artificial nitrogen fixation reactions. So nitrogen, hydrogen is the one of the resource where the hydrogen is more. In another case, the sensing, this advanced material we can use for the sensing purposes, electrochemical sensing, where the potentiometric, amperometric, impediometric, we can do it, where the signal which is proportional to the concentration of the gas. So here we have used the sulfur dioxide gas sensor. Another system, a platinum based system we have used for the carbon monoxide system. These two are the harmful gases which you are observing in the industrial zone. So this we can do on one is on gold nanoparticle, another is on the platinum nanoparticles. Here electrochemical sensor for the like non-enzymatic peroxide oxidation, because peroxide generally will oxidize in the body by enzyme catalyzed reaction. But here electrochemically we can do artificially the peroxide to the water molecule. This is the case which we have proposed. Another system which is proposed by the electrochemical NOx sensing, where the systematic will get converted into NO2 minus to NO3 minus by the oxidation process on zinc oxide, copper oxide, and zinc oxide, copper oxide alloy. Right. So these are the systems which you have proposed for some of the industrial conversions, like semicarbazide, nitrophenols. This also we can sense and convert into the less harm species. Right. So these are the examples of the deactivation and activation of the drugs. Anti-HIV drug we have modified by the one of the sulfur will get sulfone, and this will have the better antimicrobial activity. That for the improvement of the system also, this materials people are using. This advanced material like a tyramine functionalized graphene we used for this non-enzymatic biosensing properties. Right here also graphene oxide is used for the activation of ethanamide. So there are some similar examples herein. Same thing, fuel cell reaction. In one of the government project, we have worked on the development of electrochemical system for carbon dioxide reduction by considering the environmental problem. We can get back to the fuel is the idea. Once we have used the fuel, what will happen? Either carbon monoxide or carbon dioxide will come to the environment. Is it possible to work out on the carbon dioxide to get back to the hydrocarbon as a fuel? This is the idea. So what we have done, we have developed the graphene based systems, hybrid systems which are sensitive. The reason why we need to work on this to develop the new advanced material, reason behind this is carbon dioxide is having the multiple products which will work as the multiple potentials. Sometimes we need to reach to the minus 2.21 volt. This is huge potential. We cannot play in a 1 volt, 2 volt region. We need to go it beyond. In which means the like a electrochemical window of a 2 volt for the aqueous system. So the non-aqueous ionic liquid based systems people are proposing. So this case we have developed the different systems, especially we have the electrochemical carbon dioxide reduction on the manganese oxide, graphitic nitrogen, where the around 65% performance we have get. Around another system like a zinc oxide coupled with the carbon nitride, where we got a response up to 89% conversion of carbon dioxide. Some other system like a bismuth based systems we have seen, where the conversion we are reaching to the 91%. So it's alumina based system is better systems. It we have found that is 93% conversion we have observed. So by this way, if you have the capability to develop the new material as like a supercapacitor or the stability organic metal or metal organic frameworks are there, doping materials are there. So this material coupled with the electrochemistry, you can get the better sustainable material. So of course, along with the means like advanced material, if the electrochemistry if you are linking the sources to the sustainable development. Right. With this, I it's my prime duty to say thanks to the active collaborators. Of course, my supervisor, Professor Vijay Mohan Pillai, is ex-director of the CSIR NCL and CSIR SICRI, and now is acting dean in ISTE Tirupati. Professor Asepa Teddy, where I did my hydrogen production work, is the professor from the Rutgers at the State University of New Jersey, where I joined through the Fulbright scheme. And of course, the active collaborators were to share our ideas with them and improve our ideas after discussion with them. This is the case. And working hands, of course, without working hand and working brains, it's impossible. Even though we are saying if we are not doing, so nothing, that the idea will get collapse at the end. So these are the active hands which we are having. Without them, it's impossible to reach at this level. And it's supported by the fundings, different fundings from the Department of Infrastructure funding, university funding is there, UGC funding, Department of Energy, BRNS funding is there, DST SURF, HRD, DG, CSIR, DST3, United States, India Educational Foundation funding. These are the funding resources are there, where that these resources makes lab more richer. Thanks for your patiently listening. Uh, I'm waiting for the questions from your side. Hope I am ending presentation in time. Hello? Hello? Yes, yes, please. Okay. What I will do, I will share my email ID. If you anybody having any question, then they can call me. They can contact me, right? I will put my email ID also and my phone number also here. This is my WhatsApp number. You can drop me message also. You can call me at any time. No, there is no issue. For a scientific purpose, I'm always ready. Thank you, sir. Thanks.
Thanks.
Correct, sir. Shall I leave then? Okay, thank you.